Stålhammar from the Norwegian University of Science and Technology, and I'm here to give a presentation called Software Development and Safety Requirements. So what we will cover is, we'll start with risk assessment, and then we'll talk about the safety integrity level and the development process and how that is decided by the risk. We'll talk a little about the what and how standards, and we were talking about risk acceptance, and end it with a short summary. The first thing, of course, is to identify the hazards. How we develop safety critical software depends on the risk related to its operation. We're talking about operation to hazard to risk. And in order to do this, we first need to understand what the system shall do, what is the system's environment, and how will the system influence its environment, and vice versa. So, how does the system influence its environment? Well, a control system can influence the process through its actuators, which is a direct influence. But there are also indirect influences like information to the operator or the process output. And the process can influence the control system through its sensors, which is a direct influence, and there are indirect influences like process input and external disturbances. All this comes together in a generic control system suggested by Nancy Leveson. So you see there are automatic controller receiving information through sensors and through control information from the human supervisor, and it gives information back to the supervisor, and it gives orders through actuators to the control process. And the control process has inputs, it has outputs, and it might have external disturbances which will also influence it. And the supervisor, the human supervisor, has a model of the process and have, of course, the model of the automation, because that's what they act on. And the automated controller has also a model of the process, hopefully pretty much the same, and model of the interfaces. That is sensors, actuators, and controls. So this is a kind of, as I say, a generic control system. It could be it's a nice start to discuss any control system. Then we need to talk about risk assessment. So first, what is a hazard? A hazard is a source or situation with potential for harm. And hazards at work may include chemicals, electricity, working at heights, anything that can affect people's safety. And now, an unwanted event is a real situation or condition where we lose control of the hazard. So we first have the hazard, then we lose control, and then we have an unwanted event. And that brings us to the risk, which is a chance that something going to happen with a negative effect. And we're talking about the likelihood of the unwanted event, that is the hazard and where we lost control over, and the potential consequences of that event. So controls then really are the measures put in place to decrease the likelihood or consequence from an unwanted event. Remember, we have the hazards, we lose control over them, and we get an unwanted event. So the controls can prevent the event, they can reduce the loss of control, or they can reduce the effect, like provide shields or provide emergency responses. A nice way to look at this is to look at it as a barrier model. We have the risk, we have barriers preventing the risk from becoming a problem, we have handling, which prevent events from having bad consequences, and we have barriers preventing the event from sort of destroying things or reducing the effect of the event, at least. So there are barriers, and the barriers closest to the risk mostly are in the control system, but the two next set of barriers might be related to installation, to training of people, and so on and so forth. We will have another look at that model. Please keep it in mind. We will have another look when we're talking about the military standard. So several standards include control into the risk assessment, like 61508 and 62061, talking about the probability of avoiding the hazardous event, while the automotive 26262 talking about the possibility of controlling the consequences. Slightly different, but still it's about risk and control. Now, we will start with analysis. We'll start with a hazard, which is a high-level review of potential hazards. That's usually based on checklists and cover facility siting, human factors, and best engineering practices. And hazard is or should be the first step in primary risk assessment. And HAZOP, which is a study of continuous or batch processes or a procedural operation. So it's used to identify potential hazards and operational issues and recommend preventive actions. However, keep in mind, a HAZOP study is only as good as the skill of the facilitator and the team members. If you don't have good people, people who know the system, people who know the technology, people who know about hazard analysis, a HAZOP is just a good example. If you don't have these things, the HAZOP is just a good example of garbage in, garbage out. Okay? So hazard identification and operability studies form the basis for any risk assessment. It creates understanding of potential hazards, understanding of possible causes, and assessment of the effectiveness of any safeguard already in place, if any. And it's the identification of possible hazard and risk reduction measures. Now, once we understand the hazards and the causes, what can we do to remove or reduce the consequences? So the hazard, as I said, is a fairly simple thing. The first thing you do, it's a simple template, it's a 3-column table. Failure condition, then the effect of the failure. Note that effect of failure is not an accident, it's a potential accident, like a risk. And then there are some remarks. Now there are many ways to use a hazard or think about hazard. And this is just 2 examples of hazard with different foci, taken from railroad analysis. The first one is really has the focus on how to avoid. The failure condition is trackside equipment down. The failure effect is, well, this may lead to 2 trains on the same track, which might be kind of unfortunate. And the comment is talking about how to avoid. Signal and trackside equipment should not be on the same system. And on the other hand, is both consequences. It talks about the hardware error. There's a risk of train colliding. And if the signals were to stop working, the engineer might end up on the wrong track. So it's a focus on the consequences. They're still both hazards, they're still both legal, but they have different foci. I need to remember that. So we need to talk about SIL, what and why. So we need assessment of the risk in order to decide how to develop the control system. That's pretty obvious. More risk, more strict development regime, more requirements to the development process and to the system, I might add. So the SIL or a SIL will decide the development process to a very large degree. On the other hand, if we don't like what we see there is always an alternative. Specify what the purpose of the process requirement is. Find another way to achieve it, and give the assessor the idea and get his acceptance for the alternative way to meet this process requirement. You say, the purpose of this requirement is to achieve so and so, but we can achieve this in another way, which we think is simpler or better. And here is what it is. And the assessor will say, yeah, that's great, or no, that's not so great. Just remember there is a way out. SIL and development cost. The number of highly recommended requirements for the software development process. And the cost increases from SIL 2 to SIL 3. Pretty much, you see, it's not so much from the others. As we get more and more higher SIL level, we get more and more tables relevant or actions relevant, and the cost will increase. So the extra activities will have both a beneficial and a cost-adding side. You will have like more and better testing, which is beneficial and also will add cost. We'll have assertions and defensive code, which can increase our safe failure fraction and make testing easier. And these benefits are the main arguments for those who argue that there is no real cost increase. It's just a better system. But you see here, for instance, from SIL 2 to SIL 3 can be up to 100% cost increase. So let's start by looking at 6.15.08. These are our main process steps, and we start with the analysis. The analysis will decide the realization, and in the end we'll get a system which is ready for operation and maintenance. So for generic systems we obtain the safety integrity level by combining probability of unwanted event and unwanted event consequences, which is really sort of the traditional definition of risk. And then we talk about frequency or exposure and probability of avoiding a consequence. So this is summed up here. You see there are consequences, 4 categories, frequency 2 categories, probability 2 categories, and then there are 3 categories of dangerous events. So let's assume that we have like serious permanent injury, CB, and we have rare to more often exposure, FA, and we have probability to avoid is possible, okay, that's PA, and we say that this is a slight probability. Oops, that gives us to A, saying, well, no safety considerations, no special safety considerations are needed. If we have like a relative high probability, we would be forced to use SIL 1. And note that there is a issue here called B, saying that at this point, which is just all the baddies, you cannot use a single system, you need a dual channel system. So there are 3 tables that defines the process. It's the A table, which will define the process steps, which is mandatory. There are a B table, which have some more details, which is not really mandatory according to the standard, but a lot of assessors find it's mandatory anyhow. Then there is the C table, which is nominal, and there is the C text, which is just an explanation. And the C table is about rigor. And we'll get back to rigor later, so maybe we should dwell a little about it. It says R1, R2, or whatever highest available. And this is a table of rigors. We see that if we have a SIL 1 or SIL 2, we have rigor 1, talking without objective acceptance criteria or with limited objective acceptance criteria. While if we have SIL 4, then we down to rigor 3, with objective systematic reasoning that requirements property is achieved. For instance, formal proof. Then we have this A table, as I said. In this case, A1, which is software safety requirements. And for instance, for semi-formal methods, there is a reference to a table B7. And we see that like forward traceability is highly recommended for SIL 3 and SIL 4. So this will tell you SIL level and whether it's recommended or highly recommended. Recommended means just, well, that would be nice. Highly recommended means you need to do this. And then there are references here to table B7, which is the next one. And there is a set of techniques like block diagram, sequence diagram, data flow diagrams, final state machines, and so on and so forth. And you see some of them are not recommended, or at least not highly recommended, while some are highly recommended for higher SIL levels. And yeah, you see message sequence charts are not highly recommended. Since that's one of my favorite techniques, that's really sad, but oh, whatever. C22 is an explanation of data flow diagrams, so we'll see that next. So the description found in part 7 is a description. It's a data flow diagrams, have 3 aspects: annotated arrows, annotated bubbles, and operators, which are mostly AND or X or whatever. So each bubble in a data flow diagram can be considered as a standalone black box. And the reference in the standard will also contain references to literature, how to do data flow diagrams, and so on and so forth. SIL for machinery is a different standard, 62061, and the standard requires separate safety assessment for each safety control function in the machinery. So it's not looking at the total system, but it's looking at each control function, which need to have a name, a description, a requirement. For instance, according to 13849, which is a performance level, or safety integrity according to 62061. So the SIL assignment here has two steps. First, you do a risk assessment, and the question is now, will we reduce the risk through a safety related control function? If it says no, then okay, no SIL is needed. If it is, then we need to do risk estimation of a SIL assignment, and there is a feedback loop there, which is required because the provision of a particular protective measure may have effects on risk parameters. So 62061 is a fairly standard approach. You have the frequency, you have the probability, you have the avoidance, and you have the consequences. So let's assume now we have something which happens more often or less often than 2 weeks, but more often than every day. That gives you a 4 here. And probability of the event is that's possible. It's a 7. That is possible to avoid. That's up to 10. And okay, let's assume that there's permanent losing fingers or something. So 10 is SIL 1. So in this way, you have to decide what are the frequency, what are the possibility of avoidance, what's the probability, and what are the consequences. And that will give you a SIL level, or maybe not a SIL level, but just a quality management alternative. You can look at this another way. There's still the consequences and the probabilities and the frequencies. But what we get now is a PL, a performance level. And factors influencing the performance level are such things as mean time to failure for each component in a channel. And the mean time to failure for the channel is estimated via the part count model. We're talking about diagnostic coverage, common cause failure analysis, component structure, the behavior of the safety function under fault conditions. Something goes wrong. How does the safety function behave? It better behave well. Safety related software, systematic failures, and the ability to perform safety functions under expected environmental conditions. So we're back to the change between, or the communication between the system and the environment. And environment conditions can be things like heavy cold, heavy heat, vibration, lot of electric fields or magnetic fields. So you need to talk about, or need to decide, how is the ability to perform safety function under expected environmental conditions. So it will all end up with a document like this. You see at the top there is how to estimate the risk, and then there are hazards, the hazard parameters, and what we're going to do about it. So this is a nice summary. You see it all. Here's the hazard, here's the parameters which we use to assess it, assess the risk, and here's the measures. So this standard helps us to assign the required safety integrity level for each safety-related control function. It enables the design of the safety-related electrical control system, and helps us to integrate safety-related subsystems designed in accordance with ISO 13849, and helps us to validate. The next thing is the ASIL for automotive. It's ISO 26262, and hazard analysis, risk assessment, and ASIL determination are used to determine the safety goal for an item. So each item is evaluated separately regarding potential hazardous events, just for the safety of engines, or yeah. And the ASIL is determined by considering severity, probability of exposure, and controllability based on each item's functional behavior. Therefore, the detailed design of the item does not need to be known. You need to know what kind of item we have, what's its function. Like for an automotive, it might be a brake or a steering mechanism or whatever. So this is the standard. It pretty much look like the 61508. It's more detailed on the alternative ways to realize, because there are some hazards which will require other technologies than hardware and software. We can increase driver probability, and we can introduce external measures, and you see they are all related to different activities up in the analysis part. So this standard, talking about risk parameters, there are consequences, no injuries to life-threatening injuries. There are probabilities from very low probability to high probability, and there are controllability going from controllable in general to difficult to control or uncontrollable. And we'll see how we can combine this now to get an ASIL level. So you see here we have the severity, S1 to S3, and for each severity there is a probability, E1 to E4, and there is a controllability, which is these columns. So say if you have medium severity, medium probability, and high controllability, well, it's just a matter of quality management. On the other hand, if you have high severity and next to high probability and very low controllability, we'll end up with ASIL level C. Okay, this is example of methods and measures. You see that, for instance, specification of software safety requirements in natural language is highly recommended, then identified by these two plus signs for all levels, while formal notation for requirement specification is only considered highly recommended for ASIL level C and D, and it's all described in the standard section 541. This is more some kind, if you look at like model walkthrough, it is highly recommended for level A, not so much for level B, and should not be used for level C and D. So just another scoring. The military standard has a slightly different idea, although it looks pretty much like the others. As for starters, you have safety significant software functions, we have hardware, we have operators, and all these comes together to define the system risk. So the first thing we need to decide is what kind of system do we have. It can be anything from an autonomous system, level 1, to a system with no safety impact whatsoever, level 5. There's a description of how to recognize them. We have a risk assessment matrix. It's pretty standard: catastrophic, critical, marginal, negligible, and frequent, probable, occasional, and so on. And the risks are high, serious, medium, low, or eliminated. So basically the standard organizes things based on level of rigor, and the military standard arrive at the level of rigor through a three-step process: decide system type, decide risk severity, and combine these to get the software criticality index, basically telling you how critical is the software. And the software criticality index will define the level of rigor. So this is how we get the software safety criticality index: control category and the severity category. Like for instance, if we have software control category 3 and critical, we get software criticality index number 3. And This will give us the level of rigor. We see that, for instance, level of rigor 1, program shall perform analysis of requirements, architecture, design and code, and conduct in-depth safety-specific testing. While for software criticality index 5, it said once it's assessed by safety engineer as not safety, there is no safety-specific analysis or verification required. Okay. So there are really in the standard a list of things that need to be done, like all variables are properly defined and data types are maintained throughout the program. I've not read through all this. There is something kind of funny down here. It says common blocks are declared properly for each routine. Now, common blocks were quite a lot used in Fortran 2, 3, and 4. They're mostly not used now, but it still survives in the standard. What is important, though, is the priority list for activities. First and foremost, try to eliminate hazards. If that can't be done, reduce risk. And if that can't be done, incorporate engineer features or devices to reduce the severity. If that doesn't help, you need to provide warning devices. And last, you need to incorporate signs, symbols, procedures, training. So even though this is made for this military standard, it's really sound advice for any safety engineer to do it. First try to eliminate, then to reduce, and so on and so forth. If you look at the standards, they have a lot of things in common, and the most thing in common they have these different levels of risk which correspond to different activities or rigorous activities. See, the automotive we've looked at is the general one with the SIL 1 to SIL 4. It's the railway, SEMLEC, space, airborne, and so on. Should look a little about the airborne systems because they have this DAL factor, which is slightly different from the others. So development assurance level, DAL, it's sort of similar to safety integrity level, but just as for automotive and for machines, there is a DAL assigned to each functional failure condition. So the severity corresponds to the level of aircraft controllability rather than direct level of harm. And of course, once you lose controllability of aircraft, you pretty much had it. The result does not consider the likelihood of accident sequences in the initial assessment. It's just how critical is this for maintaining control of the airplane, and this gives you the development assurance level. There are, as I said earlier, two types of standards. There are how standards, focusing on how we should work, and there are what standards, focusing on what should be achieved. And myself and my colleagues, we always, when we are part of a standard group or standard committee, we try to push for this what standard, but at the present only the IMO, the International Maritime Organization, has gone all in. And here it works as follows. There are the goal-based standard, what we will achieve. There's the assessor, which works as a broker between the standard and the developer company. So the developer company look at the standard. Here's what the standard say we shall achieve. We will achieve that in the following way, and we have to tell that the assessor, and they will say, yeah, that's okay, or no, this is not okay. And if it's not okay, you have to find something else. Note, you cannot keep the assessor hostage by going to say, please assessor, how are you going to achieve this? So you have to come up with a solution, and the assessor will accept or reject it. Last issue is risk acceptance, and we're talking about two methods, ALARP and GALE. The ALARP saying we have done all that is reasonable to prevent dangerous events. And a reasonable goal is to reduce risk until extra mitigation is more expensive than the risk reduction. So this leads to a strategy where we assess all risks, rank them, try to mitigate as many of the risks caused as is economically reasonable. The GALE, on the other hand, is saying, well, GALE is short for globally at least equivalent. We have done enough so that the new risk level is not higher than it was before. In order to use this principle, we need to assess our current risk. This will help us to understand our current situation. Okay, we'll have a small look at both of them. The ALARP as low as reasonably practical. There are intolerable risks and they need to be reduced regardless of cost. There are tolerable if they are in the ALARP region. We use risk reduction measures and relevant good practices. And then there are risks that are broadly acceptable, and relevant good practices enough here. And we find out what kind of risk we have by using the following matrix. See, there are consequences here, a number of fatalities, and then there are probabilities, and we tell whether this is tolerable or not. So you find the probability and you see how many people will get killed, and it will tell you how tolerable or intolerable it is. Now, using our ALARP approach requires that we compare the cost of reducing and the system risk and the value of saving a certain amount of people's lives. So we might argue that, okay, we can spend 1 million euro to reduce the probability from 10 to minus 4 to 10 to minus 6, and that will make the loss of 11 to 15 people okay. And the question is really, is this an okay way to talk about it? I don't know. I've never been in the situation. You might be. The ALARP approach has been used where it was invented in the UK and has been used quite a lot in Europe. GALE is global at least equivalent. It started out in the French nuclear industry. So when we start a GALE assessment, you need to know all important hazards. The overlap between them for the hazard must be as small as possible, and the hazard must be split into 3 disjoint set. Hazards that apply before and after the change, those that only are relevant after the change, and those that are only relevant before the change. And there are 3 tables. The first 2 are here, occurrences and the probability. So like we have a number here and a number here, which are used as scores. So we're talking about very frequent, probable, and so on. And this probability is not the probability of the event, it is the probability that this event, if it occurs, will cause a problem. So we're focusing on causing a problem, not about the event itself. And then the third one is about severity. And the severity is referred to what is average. It says, for instance, here, the portion of occurring problems that have serious consequences are much larger than average. And we now have the hazard frequency and its logarithm, the probability that the hazard will lead to an accident as its logarithm, and we have the accident severity and its logarithm. And of course, the risk is the product, and the risk index is just the sum of the logarithms. So the global risk index can be found by summing up all the individual risks, and summing them, taking the log, will give you the global risk index. And this is a measure of the total risk of the system. So if you use scale, it's important to know the severity classification: larger than average, similar to our average, lower than our average. So we need to know our average, and we need to understand we directly compare the risk before installing the system with the risk after its installation. So we can use this in 2 ways. We can rank the hazards. We can try to reduce the hazard with the highest index first. And in addition, the text in each table tells us what we have to aim for if we want to reach a certain index value. Or we can use it as a requirement. It's up to the developer company to identify all hazards and then show that the total index is below the required value. Okay. A short summary. Well, of course, a risk assessment is of paramount importance when we shall develop a safety critical system. And the higher the risk, the more effort we need to put into all phases of the development process. This is taken care of, for instance, by the SIL and the development process requirements. However, we need to consider the system and its environment together, and that instead of making a SIL-4 system, we might reduce human access to the system's operating environment, thus reducing the risk and the SIL requirement. Last but not least, a lot of development of safety-critical software is focused on how to avoid making errors. This is, however, not enough. The requirements must also be correct, and in my opinion, we need to focus more on early development phases, and that many systems will be used for a long time period. How will we handle changes to the user's needs and changes to the system operating environment? So maintainability will be important. And we need to talk about resilience. How can we make the system survive the unplanned for and unexpected events, what Nicholas Taleb called the black swans? Because we know they will be there, we don't know when, we don't know how, but we know they will eventually show up. And we need that to make the system stay safe. And I hope you stay safe, so thank you.